Okay, so how's it going? How is problem 14 going?
Slow.
Who chose the torus? Okay. Who chose the rank 1 matrices? So wait, everybody chose the torus? Okay. Alright, that's fine. It's funny for a reason that I'll tell you after Friday. But anyway, okay, so...
Is the rank one easier?
No, it's just that the full solution for the rank 1 is available somewhere. But anyway, okay. Alright, so how far did you get? What are your questions? I mean, basically today is just discussing how it's going so far. You should have roughly half of a document. And that document will be turned in on Friday. Does anyone know how we're going to turn it? Are you going to hand it to me? Then how are you going to turn it in? Alice knows. Anybody else? Henry knows. How are we going to turn it in? Okay, me?
So I think that you would like enable some space on canvas.
On canvas.
To upload some document there.
Yeah, exactly. Yep. So turn it on canvas. Therefore, you have until 5 p.m. Right? Not until 9:50. So you also have time on Friday. And that also means you have some time for last minute questions on Friday to me. Okay. Okay, so questions. Where are you at? Where are you stuck? What has gone well? Me?
So in B, I understand how to explain the point, but where the point is in 40, but I couldn't find any like requirements to draw the surface.
Okay, so you're good with the equations and you're good with the parametrization, but how do we draw it? Okay, so let's discuss that a little bit. So this brings us to the most important subject of mathematics, which is called linear algebra. Okay, and in particular, projections. Of course, there's also nonlinear algebra. And you could also project nonlinearly. And that's one option. The stereographic projection would be a nonlinear projection. It has some nice, almost linear properties, namely all the angles are preserved. So that's kind of interesting, but it's definitely nonlinear. For example, certain points will go off to infinity. You'll miss, in fact, one point entirely. So what we have is we have some variety, right, V, and it lives inside of the 3-sphere, which lives inside of R4. And this is a 2-dimensional variety. So how do we look at it? So, were you able to generate 4,000 point or 1,000 points? No. Yes. No. Okay. Somebody who did generate 1,000 points, how did you do it?
I used a for loop in Julia.
Can you describe it to me, and I'll try to write it?
Yeah.
For.
So I just wrote like for I in 1 to 1,000. I don't think I used the variable I at all. I just wanted it to move. Because
Okay.
I used my parameterization. I just made a U and V.
Actually, I think I did the Python format. So
Yeah.
would this work?
Yes.
Yeah, and then in Julia you don't need a colon, so I'll leave that off.
So I just
By the way, what would you do if you have no idea how to write a for loop?
There's documentation on the Julia website.
Yeah, so like I could go to Google and I don't want to be safe with Google Chrome right now. What do I type? I guess for loop Julia. That would probably work. For loop Julia. If I was working in CoCalc, I would type for loop Sage Math or for loop CoCalc, and that would work. So let's do for loop Julia. And then it looks like a couple options. Here, this one is the Julia documentation, so I'll click on that. And then it'll explain how to do various things in Julia. And you'll want to go to an example that has a for loop. So you just keep looking. So a lot of your time this week should be just looking. Google search, look. Google search, read. And this is mathematics, okay? Before, it was go to the library and look up an index card. Read. Go to the library and look up an index card. Read. Now it's faster, actually, so we can solve more problems. Where would for loops be? Here we go. So that would tell you how to do it, right? Then you can just copy this and paste it and then change this code for you. So now let's go back to here. And then, sorry, I interrupted you, Mitchell. Can you continue?
Oh, so I set my parameters u and v to random floats.
I think you just do like this.
If you do that, it'll give you a random float of like any value, so it could be like super big. So here I'm gonna pull out my code to
Okay.
remember what I did. I put in the random function float 64 dot negative 1,000 colon 1,000, or in parentheses.
Like this.
Yeah.
And then end parentheses.
Yeah, and then that'll give you like integers between negative 1,000 and 1,000, but as floats. So then I divided all that by 100.
What is that?
Okay. Okay, good. So this is great. So float 64 is a type of data structure. It's a way to encode like floating point numbers, like that you can think decimal numbers. Here, this syntax is actually the same syntax as up there. It would give a list of integers. And so this is called a typecast. We're taking a list of integers and saying, please make them into floats. And then, I don't know, you didn't need this rand, did you?
No, yeah, you do,
Yeah.
because then you're just specifying the range of random numbers.
I see. Okay, so
And I think there is a dot after that.
yeah, you need the float 64 dot so that it does it to every item in this list. So basically, you have to experiment with this, and you just have to see, like, before you'd write this for loop, you just open Julia or open CoCalc, and you just try to get a list of numbers, and just see if you can do that. So you might type rand, and then see what happens, or you might type in CoCalc, you might type random, and see what happens. And you just have to search the documentation on Google, copy, paste, until you get something that you can work with. And so what Mitchell described was one excellent solution, and what I would have done would be completely different, and both of them would be fine. So this is interesting. It's really up to you. You just have to search. So that was a little, but let's continue, and I'll just say some random number, and we're gonna do this 1,000 times, and then some random number, And then what did you do with u and v?
And then I just printed values. I put in the formula for my parameterization.
Okay, and then you just typed in the formula like this?
Yeah, I put each value in the formula, I like separated it with a space. So between those I did like comma, space, comma.
Okay.
In quotation marks.
Okay. So roughly like this, except maybe here was some, the squiggle line is a formula of
Yeah.
in terms of u and v.
Mm.
Okay, yeah. And then I think in Julia you have to type end.
Yeah.
In CoCalc you don't. And so I don't actually remember these things very well. So I just Google it every single time. And you get really good at Googling how to write code. And I've never taken a formal class in computer science, and I've never had to. So I think this is the way to go, is just possibly the most important thing we're going to learn in this computational class is how to Google search to make a computer do what you want it to do. Okay, so that should be a large amount of your time, is just trying to search the internet for how to make the computer do it. Does that make sense, everybody? Okay. It's really frustrating sometimes until you get better at it with practice. After an hour of doing it, you get much better at it. You find websites that you like, and you figure out how it works. So, yeah, but it does take time. Okay, so roughly something like this. Is this your solution,
Yeah.
Mitchell? Okay. Okay, good. And then I guess your solution then, it's going to print out in the Julia terminal or somewhere, and you just copy it and then paste it into a text file.
That's what I did. Yeah.
Okay. So yeah, there are other ways, like you could create the text file yourself within Julia and save it somewhere. But in order to do that, you'd have to Google how to write to a text file in Julia, and then click and read, and then go back and then click a different link and read, and then go back to your search results and click a third, and finally the third link will have what you need. Okay, so now at this point we have a list of numbers, or at least we can generate them. And so let's imagine that we've done that we have a list of numbers. We've plugged in random parameters into our parameterization, and so we have a list, let's say, of x1 is equal to some number, some number, some number, some number. x2 is equal to some number, some number, some number, some number. Dot, dot, dot. x1000 is equal to some number, some number, some number, some number. Okay? Imagine you have this. Now we're at, finally, the problem. How to visualize. Okay? So, essentially, we need to take this list of lists of 4 numbers and turn it into a list of 3 numbers. And the question is how? Okay. Okay. And just to be clear, has anybody solved this?
Well, I was thinking you could just do a really simple projection by making one of the variables always 0, but then you probably lose a lot of information about what the shape looks like.
Yeah, let's actually think about that for a second. Let's think about that, not from 4 to 3, because when there's a problem you don't understand, the first thing to do is find a simpler problem you don't understand yet. Okay, so what's a simpler problem? Let's imagine I had a sequence of points in the plane. Not a sequence, just a list of points in the plane. Perhaps coming roughly from a circle. And I want to visualize them on a line. So I think what you're suggesting is we just go like this. Here's our projection. Just drop the last coordinate. Just literally delete the number. That 4th number, just delete it. Okay, so we can see some problems with this because we're definitely going to lose a lot of the shape. So our circle became just like a list of points. That's not great. But here's something interesting. We were thinking about, or at least I was thinking in this hypothetical example, I was thinking about a one-dimensional object in 2D projecting onto a one-dimensional space. There's basically no way to do that well, because your object has the same dimension as the space you're projecting to. Let's imagine we were in three-dimensional space and we were doing this. And we were going to project to two-dimensional space. And let's imagine we had some sort of object. Maybe it's roughly a circle. Okay? And we had a bunch of points on it. So imagine that this line I drew is actually just like 10,000 points. Okay? Now, project. Same thing, just literally drop the height. Just drop that third number. Right? Each point here is a list of three numbers. Maybe it's 5, 2, 8. And then what I'm suggesting is just drop the 8. 5, 2, 0. Well, that's roughly 5, 2. And then we're just going to plot our two-dimensional. Well, that doesn't look like 5, 2. Does this make sense? And what you'll see is that actually we roughly get the shape. That's obviously a bad drawing, but what we're going to get is like some rough shape. And it actually preserved a lot of the qualities of it. And the reason is because we had a one-dimensional object and we're projecting into a two-dimensional space, we can at least hope for some good visualization there. Okay. Mathematically, to make this precise, you talk about like the tangent bundle to this thing and how much dimension it has, because when you're projecting along a line in this case, and basically you're going to lose information when that line is tangent to your object, right? That's when a bunch of points are going to go all to the same point, and that is losing information. Does that make sense, what I'm saying? Let me think. So imagine, in other words, very rarely will this fail. But let's look at when it would fail. Let's imagine instead of this and this thing, what if I had something that lived entirely in this plane and it was a shape like that? Then when I do the same exact projection, where I forget the third coordinate, what I'm going to get is going to look in the plane like this.
But if you had the list of points, wouldn't you be able to see that the third coordinate is kind of the same?
Yeah, good point. But I mean, the nice thing is you actually don't even need to inspect. If you choose a random direction, so if you choose your projection randomly, then you're guaranteed to have a high probability of success. Okay, if your curve was random. Another option is you could change coordinates randomly. So you could make a transformation of variables, like a rotation, and then drop the third coordinate. And so then, even because the third coordinate's not random, you definitely picked the third coordinate. But if you first change variables, then drop the third coordinate, you actually get a random projection. So that's another option. Okay, so this is sort of interesting. At least I think this is sort of interesting. We're going to have the same problem in higher dimensions. But, me? Yeah?
Yeah, so instead of like dropping one data, then can I like use color to specify the value of the final number?
Yeah, great idea. So let's say you didn't want to lose all that information. You, instead of just deleting that last coordinate, encode it as a color. Right? So maybe lower numbers are bluer and higher numbers are redder. And so then you'd Google rainbow colors in Julia or rainbow colors in Sage. And then you'd just be able to make that work. Then, I mean, not only would you have a picture, but you could even maybe, even in this case, still have some idea. Although the colorful points will be on top of each other, so this will be still a problem. Yeah, okay.
Like how many points are on top of each other and the color?
Probably, well, I don't know. And I guess in this drawing, only 2 points would be. No, there's 1, 2, 3, 4. You could have as many as 4 points going to 1, which is not ideal, but yeah. Okay, so basically this is going to work because we had a 2-dimensional object and we're going to project into 3-dimensional space. So there's enough room for it. There's enough room for it to still maintain some of its shape. And yeah, that's sort of interesting. Okay, so I think we've determined that just simply dropping the last coordinate is one option. That is called a linear projection. Why? So let's talk about that for a moment. If I have the number or the point 4, 2, 3, 1, and I have the point, let's call it V, and let's call it W, 5, 7, 0, 3. And let's call L, or let's call P the map that goes from R4 to R3 that just drops the last coordinate. Send it to x1, x2, x3. Okay, so that's my map. Now, P is linear because P of CV plus DW equals C P of V plus D P of W. And you can just check that it's going to work. And in general, we could have chosen any linear projection from 4-dimensional space to 3 and use that to visualize our object. But of course, this one is the simplest. If you ran into trouble, apply an orthogonal matrix to every point and then project, and that should be better. Does everyone know what an orthogonal matrix is? Okay, so then, yeah, okay, so we're going to get to nonlinear projections in a moment, but let's do one more thing on linear projections. So what is change of variables? Variables. And how about orthogonal change of variables? Okay, first, a little quiz. If I asked you, give me a random orthogonal matrix, how would you do it? Any ideas?
I'd look up orthogonal matrix.
Okay.
Isn't orthogonal
That's a good step. Yeah.
like perpendicular, so it has to be orthogonal to something?
Orthogonal does mean perpendicular, and that does play a role in why we call it an orthogonal matrix. Absolutely. Okay, so does anyone know a 2x2 orthogonal matrix? What do I write for those 4 matrices?
Is the
Is
identity?
1, 0, 0, 1 is the identity of orthogonal matrix?
That's a good guess. Yes, it is orthogonal.
Yay.
Okay, and actually, this is a good one because what it represents is these 2 orthogonal basis vectors. The first column is the first basis vector called E1. The second column is the second basis vector called E2. Now, every orthogonal matrix can be made by transforming space, in this case 2-dimensional space, to some other pair of vectors that are also at 90 degrees. And that is how you produce an orthogonal. Well, this is what an orthogonal matrix does. Okay? And so now let's stare at this picture right here and somebody tell me another orthogonal 2x2 matrix.
I think you just apply a spin matrix to the identity and get all of the orthogonalities.
What's a spin matrix?
It's the one with sines and cosines.
Okay, and was that possibly one of our previous problems?
Oh yeah.
So, what we do is we take this thing and we remember the circle and we just rotate. Okay. And so by what angle? Well, theta. And actually that gives all of the other bases. Well, we could flip, but it gives half of the orthogonal matrices by just saying cos theta, sine theta. And then we need to rotate it by 90 degrees, which means minus sine theta, cos theta. Okay? And this is an element of what I would call the special orthogonal group on 2 dimensions. This is the group, it's an abstract group, symmetry group, of all orthogonal transformations of space. And topologically, it is homeomorphic to the circle, S1. It's actually diffeomorphic to the circle, even. So we've seen this before. Now what about rotating 4-dimensional space? Because that's what we would need to do. In order to make this dropping the last coordinate, in order to make it random, and make sure that with probability 1, we will not have the issues shown here, we need to apply some sort of change of basis. Okay? And orthogonal ones are nice because they preserve length. They preserve all the distances between our points. We would like them preserved if possible, right? We're going to project them, so it's going to be distorted a bit, but might as well preserve them at first. So what I would like you to look up, and this is now my hint to you. Look up QR decomposition of a random matrix. So if you can compute, pick a random 4x4 matrix. In Julia, this I think is literally the command rand 4x4. Maybe not. Maybe like something a little different. And then apply this. You will get something nice. So look this up. And then apply this to all your points in R4. Then drop the last coordinate. So this is a good way to project. Okay. There are other ways. You can do a different way. In particular, you could just try dropping the last coordinate from the beginning. Yeah. But remember that our object was produced in a very special way. So when things are produced in a special way, we worry. We worry about is what we're doing gonna fail for some reason that has to do with this is a very special object. It's not a random object. Yeah. Okay. It's interesting because you don't have these questions in algebraic geometry as much, but you have them in computational algebraic geometry. So if you actually want to compute with this stuff, you have to think about what could go wrong, what's random, how do I deal with how the computer's going to treat things, and sort of interesting. Although algebraic geometry does deal with randomness. In particular, many theorems in algebraic geometry only work for almost every variety. Okay? In a very precise way. You'll have theorems that work for what's called a generic variety. In particular, Bazou's theorem or like the idea that a degree 5 polynomial has 5 roots. That's a theorem, right? The fundamental theorem of algebra. Any degree 5 polynomial has 5 roots.
Except when it doesn't.
Except when it doesn't. Except when it's a very special. So any generic degree 5 polynomial has 5 roots. What could happen is 2 of the roots are the same, and so it only has 4 roots. Or 3 of the roots are the same, and the other 2 are the same, and so it only has 2 roots. So these kind of things happen only rarely. So that's sort of interesting. Okay. I would like to talk about nonlinear projections. Because if you all chose the torus, right? Okay. Have you looked at Wikipedia yet?
Yes.
Okay. But did you type in torus or did you type in Clifford torus? So let's type that in.
Is it like having Clifford the red dog?
The big red dog.
Yeah.
That's how he gets so big. Because that happens to him.
I mean, maybe he is stereographically projected in 4 dimensions.
It could be. You see that the distances are getting very distorted there, and really everywhere. I would like for somebody to figure out how to make this. Please produce this. So one thing is these little lines. That's hard to plot. Like, it's much easier just to plot the points. So just sample a bunch of points and plot them, and you should be able to get something that really does look like this surface. It doesn't have these nice lines everywhere connecting the points, but rather it'll just be a bunch of points. But you'll be able to see the shape. And then try to think about theta and rotating 4-dimensional space. So the hints I gave about the orthogonal matrices. Rotate 4-dimensional space along one parameter called theta that comes back to itself. Okay, that's really clear in rotating 2-dimensional space. We just rotate, okay, this is difficult. And that was theta, right? So I rotated my hand. How did I do it? Like this? Okay, anyway. So that's the theta I'm talking about, but now we need to do that not in a 2x2 matrix, but I want a 4x4 matrix whose entries depend on theta, and then let theta go from 0 to 2 pi, and let that be time. So at every moment from 0 to 2 pi, let's say it take 1,000 moments from 0 to 2 pi, at every moment take a picture, and then take a picture at the next moment, and then rotate 4-dimensional space a little farther, and then take a picture of the projection, and then rotate 4-dimensional space a little farther, project into 3 dimensions, take a picture, then rotate a little farther still, project into 3 dimensions, take a picture, and then assemble those pictures into a GIF. Okay? That's pretty fun. And also, it's an incredibly useful skill as a mathematician in order to figure out what is going on. Okay. And I think you should be able to produce this. And this is our object. This is here's the answer. Or one answer, right? Okay. Oh, just performing a simple rotation. Okay. In my opinion, it's not that simple to figure out how to do this, but that might be a nice goal. Okay. Let's see if they have any other visualizations. Okay, this is a torus. Let's read this. Since O4 acts on R4 by orthogonal transformations, we can move the standard Clifford torus, the special one that we all probably used, to other equivalent tori via rigid rotations. These are all called Clifford tori. The 6-dimensional group O4, why is it 6-dimensional? It's a good question. Possibly we will see that by the end of the class. acts transitively on the space of all Clifford tori, sitting inside the three-sphere. So what this means is that by using the orthogonal group, you can move our Clifford torus to many, many other Clifford tori. You can, in fact, get all of them. And because you're rotating four-dimensional space, the three-sphere stays unchanged. Like the circle stays unchanged when you rotate two-dimensional space. The circle goes to the circle. It doesn't like fly off and become an ellipse. The sphere in three-dimensional space, when you rotate, goes to itself. Similarly, when you rotate four-dimensional space, the three-sphere goes to itself, and our torus sits inside the three-sphere because, remember, if x1 squared plus x2 squared equals 1, and x3 squared plus x4 squared equals 1, then x1 squared plus x2 squared plus x3 squared plus x4 squared equals 1. Well, 2. Okay, so ours, if you use this, then it actually sits in the sphere that has radius √2. So √2 times the three-sphere is like a little bit larger three-sphere. Just like the unit circle might be here, and then √2 times the unit circle would be here. Okay. All right, this is a good hint. Also, just reading this Wikipedia page would be. Okay. Let me just say one more thing why I think you should really try to do this. Is one of the biggest areas of algebraic geometry is studying homogeneous spaces. Both of these examples are homogeneous spaces. What are they? They're a geometric object which has a group acting on it and moving it around. In particular, not just any group, an algebraic group. So the group of orthogonal matrices is an algebraic group, and it's very well studied, and it acts on your variety. And it also acts on the other variety that you didn't choose. And that group action is extremely important. In physics, you have a problem, and it's unsolvable until you take advantage of symmetry. When you take advantage of symmetry, all of a sudden it becomes possible to solve the problem. Okay? This is why the hydrogen atom is easier to understand than the helium atom, because it has spherical symmetry. Which, spherical symmetry means the group of orthogonal 3x3 matrices are acting. Okay, so this is a good thing to explore. It's going to show up everywhere. Well, it's already showed up everywhere. You just didn't know that it was there. Okay, good. Let's go back to here. I do want to say a word on nonlinear projections. Here's a nonlinear projection. Let's imagine that we're in the circle, and we'd like to project it to the line. And the way we'll do that is we'll draw a point, and wherever this point is on the circle, we're going to put it to this point where it touches the line. And wherever it hits the circle, we're going to send that to this point where it touches the line. What about this point on the circle? Where do we send that? Well, we're going to send it way out over here. This is a great projection. It's not linear, because if we do P of V plus W, it will not equal W. Okay? But it's still a great one. It's called the stereographic projection. Okay? Same thing works for, this is how we got our rational parameterization of the sphere. So same thing works for the three-sphere inside of R4. Just pick a point and send it. Yeah. Now, here's what I'll say. I'll put it in a different color. You could rotate space first by a small angle and then use stereographic projection. Okay. The analogous thing will work to send the four-dimensional space to a three-dimensional picture. Here we're sending two-dimensional space to a one-dimensional picture. But if we're living inside the circle, we can do this. Yeah. All right, I'm just going to stop talking now and just ask if there's any more questions. You can ask about this, or you can ask about the problem, because there's more parts to the problem. Can we?
I did want to ask, and this is more like logistical, because it kind of depends on if Alex also picked the torus or not, but if nobody picked the other problem.
Alex picked the other one.
Alex picked the other one, darn. I was going to ask if there was like a sample write-up that you could show us, so we could see kind of what you're looking for.
I see. Yeah, unfortunately somebody else picked the other one. I could try to think of another two-dimensional variety inside of the sphere.
I mean, you don't have to.
Okay.
It would just be nice to know kind of what
Yeah.
you want it to look like.
Oh, the sphere lives inside the sphere. So I could use the two-dimensional sphere. Yeah, okay, but the write-up is going to take even longer. Okay, here's the thing for the write-up is actually I don't want to tell you how to do it. I want to see what your abilities are to communicate mathematics. And I don't want to also restrict how you're going to do that. So some people might even write it up in a YouTube video. That would be a lot more work. But you could also become YouTube math famous. Okay? Alternatively, I really like using overleaf and writing in LaTeX because it just looks really nice and it gives me like a nice sense of satisfaction. Alternatively, you could write it in something like Word, or you could write it by hand. Writing it by hand is also pretty satisfying. But then if you mess up, you have to copy everything over again, or else it doesn't look good and then it's not satisfying. But either way, what the document that you turn in, I should be able to read it, right? So like what did the, here's the thing, there we go. Yeah, so this was my attempt. Turn in a coherent, written explanation. And then it says, record and coherently describe your progress from diligently working on the problem over the week. So what that means is I should be able to read it, and it should have words, formulas, equations, things, maps, and it should have pictures. It can have lists of points. It can have computer output. And then more words, and then some more formulas, and then more words, and then a picture, and then words. And just reading it from, like you'd read it, you're essentially writing like a section of a textbook. Think about it that way. Or really, I mean, you're writing a mini mathematical paper. Right? It's a very short paper on one example studied intensively from several points of view. Right? Okay. Okay, so we have, I think it's pretty clear that everybody can do A and B. And I think everybody can do C eventually. D, we just talked about a lot of hints on this. What about E? I'm hoping that because of previous problems, E will be easy. So if E is not easy, look back at our previous problems and just do the analogous thing, but for, it has one more entry, one more function, or one more number than the three-dimensional. Okay, then what about F? Write down an integral that computes the two-dimensional volume of some two-dimensional subset of V. Okay. I would like to point out that if you project first, you are destroying the volume. So you cannot project into three-dimensional space and then compute the volume there, which means you cannot use cross product to compute the volume of parallelograms because you're in four-dimensional space. Okay, so here is my hint. Gram matrix. What does a gram matrix do? It allows you to compute the change of variables from your parameter space to your surface by computing. This is supposed to be a parallelogram. Really didn't do a good job there. It computes this volume, and that volume is equal to the square root of the determinant of the gram matrix of the derivative. Okay. And this is what you'll have to do. There's no other way to do this. So my hint is the gram matrix. Yeah. If there is another way to do this, please tell me about it. I would really like to know. I don't think there's another way. Okay, and then what about, let's choose green. G. Is it clear what G is asking for? Okay. It's pretty weird because you have to think about the distance between a point in four-dimensional space to your two-dimensional object that's living in four-dimensional space. In calculus, you learn the Lagrange multipliers. In this example, the Lagrange multipliers will give you the answer, but you'll have to solve a system of polynomial equations, which is the subject of our class. Okay, solving systems of polynomial equations. So for G, I would say Lagrange multipliers. Okay, and good. Yes. Me?
For G, can I consider the point as 2 points in different lines and then calculate find 2 other points that is both at these 2 points.
Good question. I think I understand. It's like basically because your example is a Cartesian product. So, okay, so I was wondering this myself. Let's try to think about it a little bit right now. This is a problem I don't know how to solve, so I'm going to find a simpler problem I do know how to solve. What's the Cartesian product of this point and this interval? Or maybe how about this interval and that one? It's going to be this. And okay, so this is like our S1, and this is our other copy of S1, except obviously this is different, so I'll call it A and B. And then this thing is the geometric object A cross B that lives inside of R2, right? Because A was living in R and B was living in R. So let's pick a point in R2 and try to find the closest point. Looks like it's going to work. But because look, I mean, so what's the closest point? Well, okay, here's the problem. That's maybe the closest point in A. This is what you're suggesting, I think. And then maybe this is the closest point in B. And so in the Cartesian product, it's that point. It looks closest. Let's try another example. So this time I'll make a red point. Here. Now here is the closest point in A. And here is the closest point in B. And yeah, that looks closest again. So far, it seems like this might work. However, this is certainly not a proof, right? Me drawing little pictures. Although it's definitely the first step. So you'd have to think about, like, how does distance relate to Cartesian products in higher dimensions? And it's not clear that you can just find, because, I mean, really you're almost, I mean, we chose this A. Here's another copy of A. Here's another copy of A down here in two-dimensional space. Or alternatively, you could think that you're taking your point P and you're projecting it down here, then finding the closest point. And you're projecting it down here and then finding the closest point. So I don't know if this is making any sense, but this is me trying to answer your question. So I don't know if it's going to give the same answer. What I'll do is I'll solve it in the Lagrange multipliers way, and maybe you can solve it this way, and we'll see if we get the same answer. And then we'll have more experimental data that might suggest a theorem that is certainly in some textbook somewhere. Yeah, good question. Okay. Any other questions on this?
Couldn't you just pick a point, like with some distance to the point you're trying to find that it's closest to, and then just figure out, like, just keep splitting the set of points that you have, and it's like, these are closer than this point that I picked, these are further away?
I think what you're describing is what I would call an algorithm that would potentially give you the correct answer. Yep. Yeah.
Could we also just solve this computationally?
Well, first I'd say that these are called bisection methods. It sounds like what you're talking about. So yeah, that's something you could try. And then Miles, you said solve this computationally?
Yeah, not get an exact, it would be an exact answer, I guess. But we could, because we have a list of points, we know how to compute the distance, right? So we just run through, find the smallest.
Okay, I see what you're saying. So you have 1,000 points. Just compute all the distances to that point I gave and pick the smallest one.
Yeah.
That's a great solution. It's not the exact solution, but I bet it's going to be pretty good. Try it that way and see how it compares to mine. Yeah. That actually just suggested even another way we could solve this. You have a parameterization of this thing. So take the parameterization, compute its distance. Now you have a formula in terms of the parameters. And now you've got a two-dimensional optimization problem because your parameter space is two-dimensional. So you could also try to solve it that way. Somebody else please do that one because then we can compare and see which is the best. Does that make sense to everybody? So here, let me diagram what I just set out. So you have a parameterization, which is a map from R2 to, I guess, R4. Well, to our object inside of R4. But then we have another map to R, which computes the distance. Distance to P equals 10, 8, 7, what was that? 10, 10, 8, 7. This is a map. right? What does it do? It sends a point in R4 to what point? Well, 10 minus x1 squared plus 10 minus x2 squared plus 8 minus x3 squared plus 7 minus x4 squared square root. We actually don't need to take the square root because if you minimize this thing, it's going to be identical to minimizing the function that took the square root of it, except now you don't have to deal with the square root, which is great. Okay. And so now if you just compose these maps, let's say your parameters were t1 and t2. Now you have a map from R2 to R that you would like to minimize. Right? So this you actually did solve in multivariable calculus, right? And then you'd find the special T1 star, they usually call it, T2 star. These are the special parameters that minimize this map. So to find the closest point on our variety inside a four-dimensional space, plug these special parameters into your map, your parameterization map, and you'll get the point on the variety. So, yeah. Okay. The wonderful thing about this is that the concepts should like roughly make sense right now, but they won't fully make sense until you actually compute the answer. Until you're forced to sit down and actually do this, or tell a computer how to actually do this. And then you'll find like one little thing that you didn't quite grasp, or maybe two little things that you didn't quite grasp. And it'll actually help you to learn this much, much better. To actually find the solution to a very specific problem. Yeah. Does that make sense? Okay. Good. Let's try to think of any other questions.
When you get the basis for the tangent and normal spaces, you use the implicit formulas, and then you can also use the parameterization. But that kind of gives you bases in like that are like in different spaces. That couldn't you like do it the other way too?
There's definitely two ways to do it. One of them using the parameterization map, and the other using the equations. So, yes. And they should give the same answer at the end.
Yeah. Oh, they give the same answer. Because I was thinking, like if you do it just only in one way, then you have to know like what your points are in terms. Like if you do it in terms of the parameterization, you have to know if you have a point on the object and you want the tangent at that point, you have to know like the parameters, coordinates of that point.
Yeah. Yeah, so I guess in that way it would be in terms of the parameters of your parameterization.
Yeah.
Which is fine. And I guess the other way would be you'd have like 4 variables. And the first way you'd have 2 variables. But so you're right, I guess they are different because they're in sort of different descriptions of the same object.
Yeah. So is it easier to convert like one description of the point to another description of the point, or is it easier to find like vector bases for the normal and the tangent in both the parameterization and implicit equations?
Let's see. Which one is easier? I guess. So so they're the same, because if you use the parameterization, you immediately get a tangent space basis just from the derivative. But then you have to do some work to get the normal space. You have to solve linear equations. Now the other way, you'll see it just switches the order. The other way, if you use the implicit equations, you have a map going away from your space, and the derivative will give you the basis of the normal space, and then you have to do some work to find the basis of the tangent space, namely you have to solve some linear equations. And so everything is flipped, and one of the bases will be easy, and the other basis you'll have to solve linear equations to get a basis. Does that make sense?
Yeah.
It's confusing until you do a few examples, and then it starts to be like.
Well, could you also just figure out, like, given a point, either described by the parameters or by the 4 variables, how to describe the equivalent point in the other way?
Oh, going from one description to the other?
Yeah.
If we're just talking about the tangent spaces, so the tangent space and normal space are linear spaces, it should be equivalent to go one way or the other way. It's roughly the same. But I will say that if you try to go from a parameterization map, like the actual parameterization map, and discover the equations, that is a hard problem. It is solvable, and it's called implicitization. The other way, if you start with the implicit equations and you want to discover the parameterization map, that is in general not solvable. And that's a much harder problem called parametrization. So there's implicitization, which is actually solved. We'll see later in this course. Well, next week we will read section 4, and we'll start to see ideals. And then very soon after that, we'll solve the implicitization problem in a computer. But we'll also see how to do it by hand, although you could not do it by hand for any sort of large example. But the other way is impossible. So that's sort of, when you asked your question, I was immediately thinking about that. But if we linearize everything, linear equations we can solve. And so there we can go back and forth between the two descriptions. Yeah. Kinry, did you have another question?
Oh, I was gonna ask about the Clifford torus, because we were talking about it, and there was I'm not sure I totally understood, like, if there's a special way to rotate it to get, like, that effect where it flips inside out on itself?
Yeah.
Or, like, what exactly was happening there?
Okay. Why don't I then take the last 5 minutes of class to tell you a little bit about orthogonal groups, because this is what your question is about, basically. So the orthogonal group of the plane rotates the circle into the circle, and so we could say that SO2 acts on the circle. And SO2 is a one-dimensional group. You can see that we just needed one parameter theta to give cos theta minus sine theta, cos theta in a matrix. Now, what about the sphere? We would act on it with the group of three-dimensional rotations. This group is a three-dimensional group. Its tangent space, the tangent space to this three-dimensional group, is what is responsible for the cross product existing. Okay, so we're computing tangent spaces. Well, compute the tangent space to this. We'll do this later, maybe in 2 weeks. It's a three-dimensional group. It lives inside R9 because there are 9 entries in a 3x3 matrix. We could, when we know its equations, or if we can parameterize it, then we can do everything that we're doing for this problem. We could repeat it on this three-dimensional variety inside of 9-dimensional space. And so I guess what I'll say is you could choose, I'm now coming to your question, choose a what's called one parameter subgroup. One parameter subgroup. What is an example of one? Well, imagine just rotating about the z-axis. That's a copy of SO2 living inside of SO3. And so that copy of SO2, it looks like leave the z-axis alone, and then rotate in the xy plane. So this is a one parameter subgroup of SO3. Okay. So now we have a one parameter subgroup of SO4. That makes sense? So we're just rotating in the xy plane and leaving the other two fixed. And that would give you, this would give you the animation, right? Applying this one-dimensional subgroup to all of space would give you the animation. Now, this is quite a special one-dimensional subgroup. It might be better to first randomize everything and then apply this subgroup. But I'll leave you to experiment with this. Yeah, so one parameter subgroups are quite important. For example, they're the things that evolve differential equations, evolve the solution of differential equations. So, okay, did that sort of answer the question? Okay, good. Yeah, but you'll have to experiment with this and see what it, apply this map to those vectors of 4 numbers, which you can just put the numbers 1, 2, 3, 4 there, and then do matrix multiplication, matrix times a column vector. Okay, those are good questions. I feel like maybe now we can almost get the whole problem.